Hi everyone. In this video, we're going to continue our discussion of angular momentum. In the previous video, we derived angular momentum for a body's center of mass. In today's video, we want to derive how to define angular momentum for a point other than the center of mass, so some arbitrary point. First of all, why would we want to do this? Consider Euler's second law. We know that the sum of moments is equal to ddt of the angular momentum. And the sum of moments, we could say sum of moments on A about A. This is the change in angular momentum of A about A. What if you want to take the moments about a different point? What if we took the moments on body A about some other arbitrary point? In this case, we could do point C. Well, the numerical value of this is going to be different than if we had taken the moments about this point. So clearly this is no longer equal to ddt of HA. The right-hand side has to change because the left-hand side has changed. So we want to derive what the new expression is on the right-hand side. So where do we want to begin? Let's actually start with what we derived for HAA in the previous videos. So we want to find the angular momentum of all of body A about point C, and we are going to break this into all of our infinitely many distributed masses B sub i's. So let's start with B sub I. Let's say that the angular momentum of point B sub I about, now we're not going to do it point A, now we're going to do it point C. So I'm pulling the definition that we found in the previous video. This is the position vector from C to B sub I cross the linear momentum of B sub I. So here is the angular momentum of just the one point about of that 1 point B sub I with its mass about point C. If we want the angular momentum of the whole body, now we need to sum all of the infinitely many B sub i's. So HA about C, the angular momentum of A about C, this is equal to, we're going to take all of these quantities and we are simply going to sum them up. Oh, hello. Yeah? Yeah. Okay, go for it. So infinite summation of HBIC, right, that. So HAC, if we're doing the infinite summation on this, we're doing the infinite summation on the right-hand side. So infinite sum of P CBI cross MBI VBI. All right. So we've got a different position vector in it now from last time, but we're going to approach this in a similar way. We know that we can take some of these terms and start massaging them. Let's focus first on this VBI. What we did last time is we took VBI and we redefined it. We said, let's use transport theorem and let's define VBI this way. Now, this is true. We know that we could say VBI is, you take VA and then the relative velocity from point A to BI. We could also do this. Since we're focusing in on point C, let's do this same process, transport theorem, but let's start with the velocity of C. So VC plus omega into A cross PC to BI. This is also valid. This is another way to define the velocity of B sub I. Let's take this expression and let's insert it into this equation. So we're going to get HAC equal to, here's our infinite summation, the first position vector, CBI, cross MBI, and now we bring this term up. VC plus omega into A cross P CBI. All right, what are we going to do next? Next, I'm actually going to go ahead and distribute this into two terms. So HAC equals, here's the first term, PCBI cross NBI VC, and then plus infinite summation PCBI cross NBI omega NA cross P CBI. All right, what are we going to do next? Well, next, let's focus in on this position vector P to CBI, P from C to B sub I. And let's actually redefine this. Let's say that the position vector from A to B sub I. And let's go the position vector from A to C plus C to B sub I. So the reason I did this, I constructed it this way. We now have an expression for the position vector of C to B sub I, and let's take this and let's redefine it. So the position vector from C to B sub I, this is now equal to, and we're going to subtract the PAC from both sides. So P ABI minus PAC. And we're going to take this and we're going to put it into this expression. Now, when we do that, what's going to happen? First thing that's going to happen is this expression is going to get significantly larger. But consider that's like having this term, this first term. So let's call this expression number one. This first expression is going to break into two. So number one is going to become two terms. And then we're going to take this and we're going to put it into this second one. So here's expression number two. And number one, this one's going to become two terms. And then expression two, well, this is like having A plus B times B, let's say C plus D, even though it's actually the same thing. Yeah, okay, so we could say A plus B. So what's going to happen here is that we're going to FOIL this. We're going to expand this. And this one we're actually going to get 4 terms out of. Now, in a standard FOIL method, you end up with a 2AB term because these are scalars. That is not going to happen in this one because of these cross products. So here's what's going to happen. We're clearly going to get 6 terms out of this whole thing. So what I want to do, I'm going to clean this up. And I'm actually going to read these 6 terms off of some notes because there's just so many of them. And I'm going to erase this thing and I'm just going to write it all down. The previous expression we had was HAC is equal to, and we had one expression plus the second. We said that the first expression was going to give us 2, and the second expression was going to give us 4 terms. So I want to focus first on the 2 terms that are rising out of that first part. So HAC equals. If you take that position vector that we had, and I'll write it here, we said that P CBI was equal to, we wrote this as P ABI minus PAC. If we take that and we put it into these 2 terms, and then we expand, here's what we're going to get. And I am going to do a little organization here to make it clear what we're doing. So here's our infinite summation, and this one comes out to be P MBI, P ABI, and there's a cross product with VC. And then the second term minus, this one is PAC Here's our infinite summation MBI cross VC. And we could, if we wanted, I could actually take this infinite summation of MBI and I could move it all the way to the end if I need to. In fact, let's do that, just to make it a little cleaner. So cross VC, and here is our infinite summation of MBI. We can do a little simplification on both of these. We have actually seen from the previous derivations, remember this came from definition of center of mass, we know that this is equal to 0. And if you have a concern about this cross product with VC on the right hand side, if you remember your cross product rules, you can reverse the order of a cross product and just make it negative. So we could say that negative VC cross infinite summation of MBI PBI, that's actually the same thing as this. We just reverse the order and put the negative, and this is equal to 0. So it actually doesn't matter that the cross VC is on the right hand side. Oh, yeah, equal to 0. Now, what about this term on the right? So this is just MA. So HAC is equal to, now again, these are just the first two that are coming out of expression number 1. So this one is 0, and then this one, we usually write it this way, PAC MA cross VC. I'm going to say plus dot, dot, dot. And the dot, dot, dot are the 4 terms that we have yet to deal with from that previous expression. This first part, this one, there's no more simplification we can do with this. So whatever form we come up with for our final angular momentum about the arbitrary point, this is going to be tacked on. But consider if we're doing an example like a pendulum, and if the pin joint is that arbitrary point that we're taking the momentum about, if the pin joint is, in this definition, this derivation, if that's point C, well, the velocity of the pin joint is 0. So there are times when you're going to be looking for angular momentum about arbitrary points where this term conveniently goes to 0. Now, in general, it doesn't. And whenever you're working with this equation, you should write the full equation. And then if it does go to 0, okay, then you just show that it does. So let's, I'm actually going to clean this up, and I'm just going to take this expression and move it to the top, and then we'll show those other 4 terms coming out of expression number 2. So HAC is equal to, I'm just going to bring this up, minus PAC cross PAC MA cross VC plus. All right, and I am definitely going to read these off of my notes. So there's 4 of them, and here they are. Here's the first one. Infinite summation of MBI, PABI, cross omega NA, cross PABI. Next, minus infinite summation of MBI, PABI, and let's just put some parentheses around that one to show what we're about to do. And then this is cross, and I'm going to put this part in parentheses as well, omega NA cross PAC. Consider that the omega NA and PAC are constant. With respect to the summation, we could reverse the order of the cross product as we did a moment ago. We would change the sign, and clearly this piece is going to equal 0. Next, minus PAC cross omega NA cross infinite summation of MBI PABI. And tell you what, let's put that one in parentheses. So we can show what's going to happen. We know that that now is equal to 0, and these are already on the left side. So this is equal to 0 as well. And here's the last term, plus PAC cross omega NA cross PAC, and here's the infinite summation all the way at the end of MBI. So this first one up top, this one was left over, and then here are the 4 terms that are arising out of expression number 2. And the 2 in the middle, we've shown that the 2 in the middle equals 0. So what I'm going to do now is I'm going to put all these things together. But before I do that, here, I'm going to put the plus right here. If you look at this one that I'm highlighting, and if you go back to our previous derivation, what you will discover is that this bit is actually this. This is IAA omega NA. So this is that vector triple product that we eventually redefined as the inertia dyadic dotted with the omega NA vector. So what does that mean? That means that buried in this expression, right, in all of this nasty math, where we go looking for the angular momentum of a body about a different point, buried inside of this is in fact the original angular momentum that is now being modified by 2 expressions. This expression survives, and this expression survives. The other 2 in the middle, these went to 0. So let's take this and let's just clean it up. And let's write it all, write down everything that we have up until this point. All right, so HAC. So this is going to be minus PA to C, MA cross VC, plus IAA omega NA plus, and now here's that third term again. And what I did is that infinite summation that was hanging out at the end, that's just MA, so this is MA PAC cross omega NA cross PAC. Now, this one, this is again a vector, I'm just going to write VTP. This is a vector triple product. So we had to deal with this last time. And consider that when we did, when we had this vector triple product in the previous derivation, it ended up looking like this, right? It ended up working out that there was some kind of 3x3 dyadic that we could use to represent all of the positions, and then that one had the omega in the middle as well. And that omega ended up on the right-hand side. So here's what we can do. Let's look at this position vector from A to C. And recall in the last video, we actually had to just make some assumptions about position vectors, and we wrote it in a very general way. So I'm going to do the same thing. I'm going to say, let's just say that the position vector from A to C is equal to some generalized position. So let's say AX in the X hat A, and AY in the Y hat A, and AZ in the Z hat A. Similarly, we can make an assumption about omega in A, and omega in A is going to be omega X in the X hat A, plus omega Y in the Y hat A, and omega Z hat A. And if we take these assumptions and consider what that vector triple product is going to be, so I'm just going to say that VTP, the vector triple product from just a moment ago, if we write that using those identities that we have for it, here's what we get. So we still have this scalar mass on the outside, and it's the position vector A to C dot A to C multiplied by omega in A, and it's minus PAC dot omega in A times PAC. So what we can do, we can actually perform this expansion. Notice that this time around, there is no infinite summation on the outside. We can literally take these position vectors, we can just plug them in and see what arises out of this. So here's what's going to happen. If you take these and you put them in, you get the nice long expansion. It ends up having a very similar form to what we saw in the previous derivation. So feel free to go back and look at that video. I'm going to cut to the chase, and I'm going to show you how this thing simplifies. So just as we had with inertia, where we turned it into a dyadic, we're going to turn this one into a dyadic as well. And the dimensions are the same. It's going to be 3 by 3, and the terms are going to look like this: ay squared plus az squared. The next one is minus ax ay minus ax az, and let's see, minus ax ay. Now in the middle is ax squared plus az squared. This one is going to be minus ay az minus ax az minus ay az, and ax squared plus ay squared. Excuse me. And then all of this multiplied by still the scalar mass. This is our vector triple product. It's turning into this. And then it's this 3 by 3 dyadic or matrix, however you want to think of it. And it is dotted against the omega in a vector. So omega x, omega y, omega z. So if you go back and look at the previous video, if you look in your notes, this very clearly has a form very similar to an inertia dyadic. And the units are the same as well. We have kilogram here from the mass. We have meter squared for every one of these individual terms. And then the angular velocity is going to give us radians per second. So when you multiply all of this together, you get kilogram meter squared per second, which is the same units that we had from the previous derivation. So just like we did in the previous one where we said, all right, let's give these things names. Last time we called it inertia. This time we call this, we give it the letter capital D, and this is arising from the position vector from A to C. So we give this the capital D with the subscripts AC. And DAC, it does contain the MA. So the MA is distributed to all of these individual terms. This is called a displacement dyadic. So it has the same dimensions as your inertia. It has the same units, kilogram meter squared. And we're going to take DAC and we're going to dot it with omega in A. So this is what your vector triple product has become, is this displacement dyadic times omega in A. Now, how do you build the displacement dyadic when you're working a problem? It literally comes from the position vector from A to C. So if you have some general body, I'm going to draw some potato-shaped thing, and you know where the center of mass is A, and you're working some problem, and the problem says find the angular momentum of this potato about some arbitrary point C. Well, then you find the position vector from A to C. That position vector has 3 components, AX, AY, AZ, and they go in to this dyadic. You literally take the dimensions, the geometry, and you make this 3 by 3 matrix, a dyadic, and then you multiply it by omega in A. So let's take all of this stuff and let's put it all together now. remember the original point of all of this? We wanted the angular momentum of some body A about some arbitrary point C. And we ended up having three terms in this expression. We had minus PAC, MA cross VC. We had the original angular momentum, IAA, omega NA, and now we have this new term coming from the vector triple product. And that's the displacement dyadic from A to C multiplied by omega NA. We can actually do a little simplification here. Consider that IAA and DAC, these are both 3x3s. And this is the same omega NA. So I'm going to say that HAC is equal to, do not forget this term, minus PAC MA cross VC plus, we can combine these, IAA plus DAC multiplied by omega NA, and in fact we can even rename that. So HAC equals, bring this down, and what we're going to call this now is a new inertia matrix. This is the effective inertia of body A taken about point C. So we can call this IAC, omega NA. This is the final form of our equation. And what I actually recommend, if you're working a problem, homework, exam, something like that, and the problem statement says, find the angular momentum of body whatever about point whatever, my advice is you can actually start with this. Clearly you have to do all the rest of the definition of the problem. You got to put points and frames and position vectors, etc. But if you're having difficulty remembering the process, you can actually write this equation first. The angular momentum of A about C is equal to, don't forget this, but A about C, okay, that's the inertia of A about C times the angular velocity of that body. Well, from here, what do we do next? Well, what is A about C? Okay, it's this. So you write another definition underneath and you say, all right, I know this expression. I know that I need to construct IAC. I know that that's IAA plus displacement dyadic from A to C. The IAA, this comes from standard equations for the geometry of the body. So what about the displacement dyadic? Well, displacement dyadic is a function of the position vector from A to C. If we're going from A to C on the dyadic, we need the position vector from A to C. If we're doing angular momentum about point J, then this would be the inertia of A about J, and that would be the inertia of A about A plus the dyadic from A to J, and the dyadic is formed from the position vector from A to J. So this actually ends up being a fairly recipe-esque process if you can just remember the details on how to put all this information together. Now, what we have just done, this has a name. This is the parallel axis theorem. The parallel axis theorem, you might have seen this simplified in other classes to be something like ml squared. That's a scalar form of it. This is parallel axis theorem for 3 dimensions. So you have some generalized body, generalized position vectors, you make a dyadic out of it. If you're moving in 1 dimension only, it does end up being something like your inertia plus an ml squared term. All right. So that's it for the derivation of parallel axis theorem. I do want to do one more description of a problem. I want to talk about composite bodies in this video. So now that we understand how to do this, let's talk about how you combine various types of geometries into single rigid bodies. So let me clean this up. In this example, we have this rigid body. This rigid body is shaped like a Tetris L, right? You're not going to find this shape in the inside cover of your textbooks or on Wikipedia. What we can do, though, with these types of objects is we can recognize that this L shape is actually made out of a combination of two sub-bodies which do fit nicely into basic geometries. So let's say that we say the one on the left is body A and the one on the right is body B, and together they make body C. Suppose that we wanted to find the angular momentum of C about C. Now, we know that there exists some center of mass for this whole thing. It might be right here, for example. It could be point C. We know from previous definitions that the angular momentum of C about C, this is equal to ICC omega into C. But how do we get ICC in the first place? The whole thing together isn't any of the standard geometries. The individual parts are. So let's say this. Let's say that ICC can be made from the inertia of A and the inertia of B. However, we cannot do this. And the reason we can't do this is these two inertias, IAA, well, that's the inertia of A about point A, and IBB, that's the inertia of B about point B. And remember, this is a part of Euler's second law. This is connected to the sum of moments on the body. So if you attempt to add these things together, that is akin to taking the sum of moments on A about A and adding them to the sum of moments on B about B, which makes no sense, right? If you're going to add moments, they have to be about the same points. Same with inertia. You can only add inertia if they're taken about the same points. Well, we just learned parallel axis theorem, which means we can now do this. The inertia of the whole thing of ICC, this is equal to the inertia of A about C plus the inertia of B about C. If we take the inertia of A and we move it to point C, if we find the effective inertia of A about point C, if we find the effective inertia of B about point C, then we can add these things together, and that will give us the inertia of the entire body C about C. If you take this geometry and you put it into a CAD software and you let the software discretize it and calculate the inertia numerically, you'll get the same value. Numerically the same value, right? According to the resolution of the mesh, etc. So how would we construct this? We would use our parallel axis theorem. We would say that IAC is IAA plus DAC. And then IBC is IBB plus D from B to C. So we would find the original unmodified inertias for body A, body B. We would construct the two displacement dyadics, and these are going to be different. The first one is a function of the position vector from A to C, and the second one is a function of the position vector from B to C. And if you know the geometries, you can construct these dyadics. All right, so this is called a composite body, where you take these and you put them together. Hey, look at that, see, composite body. So you will see in your homework problems that you're going to have bodies of, you're going to have composite bodies that are made out of combining different shapes, and it might be a sphere attached to a rod, attached to a block, attached to something else. The best approach, or the easiest approach, when you're doing this by hand, when you don't have the advantage of CAD software, break it into the individual components and find the inertia about a shared point, and then you can linearly add it together. And then you just take the angular velocity of the whole thing and you just multiply by that dyadic, and boom, there's your answer.